All right, everybody, welcome back. Hope you had a great weekend. This week, we're going to be talking about coastal hazards, coastal processes, erosion, and then that'll be a good segue for at the end of the week where we're talking about climate change, because a lot of the stuff that happens on the coast is related to climate change, and the two are very interconnected. So we'll talk about that this week. If you're missing any assignments, as per usual, email me, let me know. If you need an extension for the deadline, I'd rather you get your work done and understand it than rush you and to meet those deadlines. So I'm flexible, but make sure to communicate with me. I have your exam ones graded. The grades will be posted this afternoon because I still have 2 students that need to take the exam, so I can't discuss the exam until tomorrow, but all the grades will be posted. I will say everybody will get automatically 1 point because there was a mistake on the Scantron sheet, so it automatically marked everything wrong for that specific answer. So everyone's going to get a extra point for that, and most likely it'll be curved. So yeah, we'll address that tomorrow. Keep in mind, we also have exam 2 at the end of the week, so please be studying for that. I will say prior to exam 1, I had 1 student come to office hours and ask for help and clarification. That student ended up doing very well on the exam. So I'm not saying there's a correlation, but it definitely didn't hurt their grade coming to office hours, getting help, and getting some more clarification. So if you're unclear about some of the concepts we're going over, yeah. Oh, okay. Yeah. So if you're unclear about any of the concepts we're going over, it's a lot of information to throw at you in a really short amount of time. Please come to office hours. Please email me and set up an appointment. I'm here to help you. I'm here as a resource for you. So I'm not just here to lecture at you. I want to help you understand this stuff. So keep that in mind going into this week, and next week we'll also have exam 3 because this is a very short class. It's 5 weeks. So we're almost done, everybody. What was your question?
I was just going to ask what topics.
That's a good question. I have that somewhere. It'll start with tsunamis, and I think it will cover coastal hazards. So all of last week and a little bit of the week before. So tsunamis, volcanoes, rivers and flooding, and then it should cover coastal processes, which will be today and tomorrow. And then the last exam will be climate change and the rest of everything else. So just keep that in mind. So start with tsunamis. It'll help to review some of the earthquake stuff too for exam 2, because earthquakes are frequently related to tsunamis. So just brush up on that. That might help too. Emma, that's a good question. Thank you for posting that in the chat. So the grade that will be posted, initially, it will be, initially I'm going to input it with the 1 extra credit point for that mistake. And then after I have all the exams input, then I'll curve it. So eventually you're gonna have your curved exam grade in Canvas. If you have, whenever you get your exam back tomorrow and you have questions about it, I'm not going to dedicate class time to go over the exam just because we got a lot of material to go through. So if you have questions about your exam, if you feel like a question was unfair, and you can approach me about that, and if you can make your case, maybe I'll give you a point or something. If you have questions about your exam after you get it back, come see me in office hours or make an appointment, and I'll be more than happy to explain it to you. So I think that's all the bookkeeping stuff we have. Okay, any other questions before we get started with lecture? Okay. Where are we? Okay, so this week, obviously, we're talking about coastal processes, erosion. It's something I worked on when I was doing a lot with my master's. Specifically coastal geomorphology, which ties a lot into erosional processes, coastal resiliency. So this ends up being a very, very important topic for a number of reasons. Number one, as we've mentioned, people live near the water, and the coastline is where the water is. So obviously, as we continue to build on the coastlines, we're going to get more and more hazards associated with coastal processes because more people live there. Delaware is home to about 96 miles of coastline. So as you can imagine, the Delaware Geologic Survey, other state agencies, they're really concerned and really focused on coastal processes and how that affects Delaware's economic needs, its infrastructure needs, its emergency medical services. A lot of these things tie into how the state runs. So they invest a lot of money in coastal resiliency, and they're investing a lot of money into research and development in protecting those coastlines. So this picture is from Hurricane Michael. Hurricane Michael hit the panhandle of Florida pretty hard. So this is, it's not Miami-Dade, forget where it is. Can't remember off the top of my head, but just a comparison from left to right. Hurricanes we get on the East Coast pretty frequently. We don't get a lot of tsunamis, as you remember from our tsunamis lecture, but we do get a lot of hurricanes all up and down the East Coast. That's mainly due to oscillating air in the Atlantic Ocean, just off the coast of Africa, creates tropical depressions that eventually form hurricanes. And those hurricanes can travel any number of directions. But the most at-risk places are on the coast, obviously, because once they hit land, they start to lose their energy. So coastal communities are hit the hardest by these events. So like 2017, at the time that this article came out, was the most expensive in US history. That was in 2017. 2020 ended up being even more expensive than 2017. So it isn't just the human cost, which most people can deal with a hurricane nowadays. You get a hurricane warning, the governor says, you should probably evacuate. And then it's up to you as the individual to leave or not. So you probably board up your houses, you board up your windows, maybe you throw some sandbags down, you get out of there, and then you come back and assess the damage. And these obviously cause a lot of damage. So during this period, we had, in 2017, we had Harvey, Maria, and Irma, which are really close together on the alphabet. If you're not familiar with how hurricanes are named, whenever a tropical depression forms in the Atlantic, it gets a name based on the first one of the season, starts with A, it goes all the way to letter Z. And if we keep getting more than 26, we recirculate through that alphabet. So not every tropical depression makes it up to hurricane status. So the fact that we had so many real close together is pretty concerning. Just because we get a lot of tropical depressions. Sometimes they turn into tropical storms, but they don't always make it to hurricane status. So the more hurricanes that we get closer together is a concerning trend. So Hurricane Harvey hit Houston pretty hard. Irma hit Florida Keys. A lot of the Caribbean was threatened pretty horribly. And then we had Hurricane Maria, which you probably remember, just almost decimating Puerto Rico. Since it's an island, it's really hard to get power back on because everything has to be shipped in over the ocean rather than just trucked down the I-95 corridor, as you can imagine, with the continental United States. So it's a lot harder to help out island nations during stuff like this. So that total estimated cost was $202.6 billion in damage. So as you can imagine, if you can make more resilient coastlines, if you can build more resilient coastal communities, that would be a great way to adapt. And if you can put forward a kind of pricey upfront cost, you may lower your price of recovery. A lot of people don't always focus on the upfront cost. They don't think about how much it's going to cost just to repair everything. It's always going to cost a lot of money to do that. So this is from 2017 to 2020. So over here with 2017, we had 18 tropical depressions. So almost the whole alphabet right there. 17 of those made it to tropical storm status. 10 of those made it to hurricanes. 6 of those made it to major hurricanes, which means category 3 and above. So the hurricane scale, we have 1 to 5. Cat 5 is pretty devastating. If I remember correctly, Katrina was a category 5, I think, off the top of my head. Yeah, that was a pretty devastating one, as you can imagine. So 2018, we have 16 tropical depressions, 15 tropical storms, 8 hurricanes, and 2 major hurricanes. So it's a little lower on the scale, which is better. Then 2019, 20 tropical depressions, 18 tropical storms, 6 hurricanes, 3 category 3 plus major hurricanes. And then with 2020, we had 31, which is the record high, and it tied with 2005. We had 30 tropical storms. So out of all the depressions, only one of them didn't make it to a storm status. And then about half of those were hurricanes. So 431 fatalities, $51.46 billion. So it's starting to add up real fast. So that's from hurricane season, which starts in the around late June probably, but we can also get some pretty serious winter storms on the East Coast of the United States. So this was from Winter Storm Jonas in 2016. So we had some pretty high storm surges in Delaware and New Jersey. As you can imagine, New Jersey and Delaware experienced similar storm surges just because of their proximity to the Delaware Bay. So on that morning in January, the water level at Lewis rose around 9.27 feet. So really high watermark for Lewis. And that's mainly because storm surge at 4 feet combines with the tidal cycle. So we get even higher amounts of water. Let's see, how many places were impacted? We had Great Channel at Stone Harbor, we had Cape May, and we had everywhere surrounding Delaware Bay. So we had significant flooding in the winter. One good thing about winter storms is you don't have to deal with tourist traffic, so it's a lot easier to get repairs done. But as you can imagine, if we were in the heat of the summer, that might be a little more difficult. So one of the problems that we have with evaluating coastline risk and hazard is that coastlines are not evenly distributed. Look at how much land is in the northern hemisphere versus the southern hemisphere. Even though there are huge population and financial centers in the southern hemisphere, Buenos Aires, Sydney, Australia. These are huge, huge population centers. South Africa, another huge one, but they don't have a lot, as much coastline as we do up in the northern hemisphere. And we can graph that distribution. So this is looking at millions of square kilometers of land areas versus ocean areas based on latitude. So remember, whenever you're talking about latitude versus longitude, lat is flat. So we're going up this way with those latitude lines. So we can have so much more land area distribution up in the northern hemisphere. And if we just look at the map, it's easy to see that. We've got most of North America, actually all of North America, including Central America. We've got all of Russia, all of Europe, most of North Africa, most of Asia. So all the land masses up here sequestered in the northern hemisphere. Southern hemisphere, not so much. We've got Antarctica, but luckily nobody lives there except a couple of unlucky scientists that have to study in the cold winter months there. But we've got a very uneven distribution of land and ocean when it comes to the surface of our Earth. So we've seen images like this before when we're talking about plate tectonics, specifically the seafloor and how it opens up through seafloor spreading. And we can see those plate boundaries clearly on this map. You can see the Mid-Atlantic Ridge over here on the right, this irregular line that goes down the Mid-Atlantic. You can see the Pacific Ring of Fire and all those divergent boundaries that surround it, especially around the Indian-Australian plate right there. So we have a lot of these different areas. Now, this specific image is showing areas of elevation. So the highest elevations are obviously going to be land because they're above the surface of the water. But as you can see at those mid-ocean ridges, we've got a little bit more yellows and oranges. So we're a lot higher in elevation. But if we look at the margins of the continents, we can see this like red outline. So what is that? That's actually part of the continent itself. It's the continental shelf. So we have these areas of the continents that they're still underwater. You're still not going to consider it part of the coastline because you can't see it standing on the beach. But if you were to walk out, you would still go down this gradual slope and it would still be part of the continent until you reach a steep, steep drop off. And that's where you get into the deep ocean basins, deepest parts of the ocean. There's this steep drop off from these continental margins, these continental shelves, into the real oceanic crust that you see, that real dense, heavy basaltic crustal rocks. So this is what that looks like in a cartoon image. So one of the first places that we found this was whenever we were mapping out the Hudson River. We noticed that the channel itself of the Hudson River continues even underneath the ocean, which is not what you would expect. Honestly, you'd think once it meets the ocean, that's it, that the channel's done. But the continental shelf is a relic of lower sea levels. So we have these gentler slopes. We have this large, really long, almost 200-kilometer long shelf here, and we can clearly see this indent, this channel cut into the shelf itself. That tells us that the Hudson River used to run that entire course before it met the ocean. So that tells us that the sea level had to be lower at some point, because water is always going to flow from high elevation to low elevation. And if it continues to flow and create a channel, that means it had the gradient to cut into the rock itself. So we can kind of map out and time out instances of lower sea level, of higher sea level. So obviously we can tell that the sea level today, based on the coastlines of New Jersey, Connecticut, are higher than they were whenever the Hudson River had started to form. So what causes the sea level to change? Could be ice sheets. Remember, we had the Pleistocene glaciation where almost all of Northern America, all of Canada, all the way down to northern Pennsylvania was just covered in these large ice sheets. That's locking up a lot of the water. It's not flowing into the oceans, so the ocean total water level is going to be a lot lower. Whenever we have a lower water level, all the water that's flowing in our rivers is going to start to incise more and more into the rocks. And that's why we can still see that Hudson Canyon today. Okay, so we have the continental shelf, that real gentle sloping part. And then we have the continental slope, that real steep part right before it meets the abyssal plain. So we have all these canyons that were carved from all these really turbid water currents. And even though they're below the water right now, those currents are still active in moving some of that sediment out. As you can imagine, it's a lot easier to move saturated sediment than it is like dry sediment, just because it's in the water, there's a little bit more fluidity, so it's able to flow a lot more. So you get these alluvial fans at the base of these continental slopes. So if you map out these fan deposits, you can tell where the source rock was coming from, which is pretty cool. But we have all these submarine canyons along this continental shelf, going all the way down this continental slope, the steep part, and depositing stuff in the abyssal plain. This is where we're meeting the lowest energy environment. So all that real fine grained stuff is finally going to fall out. So those alluvial fans, like silts, clays, real fine grain, not as fine grained as you'd find upstream. Okay, now we've gone from the continental shelf down the continental slope into the abyssal plain, or the deep ocean basin. This is what makes up the majority of the ocean floor. The continental shelf, even though it's hundreds of kilometers long, it's compared to the abyssal plain, it's nothing. It's real small, real narrow. So here we're about an average depth of 2.5 miles, 4 kilometers. Really broad, really flat. We're not getting any steep gradient change. There's no energy there to create canyons and valleys. There's nothing going on there geologically except for deposition. So that's where we're getting all this sediment that falls off of the continental slopes, falls into these plains, and eventually it all levels out in a nice flat area. Then eventually, if we keep going from the abyssal plains, we'll reach a subduction zone. That's where we get these deep ocean trenches. Remember, as the subducting plate is going under the overriding plate, it's going to pull that overriding plate down a little bit. That creates that trench, that really, really deep ocean part. So the Marianas Trench, almost 7 miles deep, super, super deep. So why do oceanic trenches form? What's going on to form oceanic trenches? Who can tell me? Not you, Adam. D, very good. Formed by subduction. We've got subduction zones, they're pulling that plate down in our oceanic crust, densest crust. So denser things want to sink. So we got the deepest parts of the ocean formed at subduction zones where we're getting that pull into the earth. So don't forget, not only do we have subduction zones, we have mid-ocean ridges. Mid-ocean ridges form and have these patterns like seams on a baseball, where we have this long general trend of the linear feature of the rifting. But because we're pulling stuff apart at different places and different angles, we're also going to get a bunch of transformed boundaries. All these blocks of rock sliding past each other in a strike-slip motion. So we've got the general trend broken up by these transformed faults and all these transformed boundaries. So when we get to from the slope, we're going down, get to the abyssal plain, we're deep, 4 kilometers deep, 2.5 miles deep, very flat. Once we get back to the mid-ocean ridges, we're going to start to rise in our elevation. That's because we're building up all of that magma that's coming to the surface. We're pulling the earth apart, allowing magma to come up. It hardens, it cools, and it piles up along those those boundaries. So it's called a ridge because it's literally just a mountain ridge underneath the ocean. So this is where we get those higher points in the middle of the ocean. So as I said, when we talked about plate tectonics, I said plate tectonics is the foundation of pretty much all geologic knowledge today on a large scale. And that's true for coastal processes, especially coastal processes, because plate tectonics and plate boundaries, that's where all the geologic energy is. That's where things are happening. Things are moving. Things are spreading apart. They're crashing together. That's where all the exciting stuff is happening. So based on your proximity to a plate boundary, you're going to have different coastal processes associated with that. So we're going to have two different types of coasts that we're going to talk about. Passive coasts is number one. So passive coasts, we're not near a plate boundary whatsoever. Nowhere even close. So we're not seeing any volcanism. We're not seeing many earthquakes. We're not getting those big, exciting geologic events. What we are getting is we're getting a fuck ton of sediment, just so much sediment. All the sediment on Earth is at these passive sources. Just depositing everywhere along the coastline where there's not a lot of geologic activity. So we're just getting constant sedimentation, building up of the land, building that coastline out. So this is where we have the widest continental shelves. So the east coast of the United States, very wide continental shelf, around 200 kilometers. And because we have this wide continental shelf, we've got a lot of building up that we can do there. So we have all these nice sandy beaches along the coastline, and we can develop all these interesting coastal geomorphic features. Barrier islands and sandbars are kind of intertwined there. All a barrier island is, it's a sandbar that was just cut off from the land surface. So sandbars develop as like these long peninsulas of sand. As the wave action is building up those deposits of sand, they'll develop into these long linear features. If those features get cut off, that's how it turns into a barrier island. Barrier islands are of particular interest to people whenever they were colonizing North America, just because it's called a barrier island just because it protects that back bay. So if you wanted to dock ships, that was a perfect place to do it. It was away from the wave action, gentler waters, a good place to build a harbor. And then we have spits. Spits are these parts of the beach where it's extended from the actual coastline. So if you're familiar with Cape Henlopen, that's a spit where it has this hook shape to it. Comes off the land and it just has this weird extension. So that's passive coasts. Now we have active coasts. Now we're closer to a plate boundary here. We have a lot more geologic activity going on. We have a lot more uplift because we may have subduction. So we have that overriding plate is getting pushed up a little bit. Think West Coast, the Cascade region. So if you go up the coast of Washington, Northern Cali, this is kind of what you're going to see. You're going to see all of these big rocky features jutting up high into the air. So as we're building up this coastline through uplift, we're exposing new rocks and we're creating a new coastline, a very rocky coastline. So you don't have a ton of beaches at these active plate boundaries. Most of those beaches that you see on the West Coast are engineered, bring in a lot of sediment and a lot of sand to create those beaches along Cali. But once you get to Northern Cali, there's nowhere really to put a beach where it wouldn't be eroded away immediately, just because there's so much wave action. So instead of deposition, we're going to take all that sediment away. We're going to get erosion. Remember, deposition is the depositing and placing of sediment. Erosion is taking all that sediment away and moving it somewhere else. So this is where you get these sea cliffs, and you can have constant wave action is going to form like sea arches, and eventually it'll winnow out the center of those, and then you can get these sea stacks. So if you go to Washington, Oregon, you see a bunch of these like in a line going off the coast. So that can tell you a lot about how much is eroded away. Eventually, at some point, that rocky coastline was all the way out to that third sea stack there that you see. Just a huge amount of rock just eroded away just by water. Like I said before, water is the most powerful thing on Earth. Give it enough time, it'll eat through anything. So this is where we get rocky shorelines, sea cliffs, real picturesque areas that people like to live. So let's think of the Mid-Atlantic. What kind of coast is the Mid-Atlantic? Delaware specifically. Are we active or passive? You can just shout it out. Passive, very good. We're not close to a plate boundary at all. The nearest plate boundary is 1,500 miles away at the mid-ocean ridge. So 1,500 miles is a long way to have any form of geologic activity. So if we look at Delaware, that matches what we said. It's a passive coastline, so we're going to have a lot of sandy beaches, a lot of gentle slopes. As we mentioned, Cape Henlopen, you can see that it's a spit, so it's pulling sand from the rest of the shoreline and pulling it out into Delaware Bay. That'll be helpful whenever we're looking at currents, just because the shape of the spit indicates the direction of the current. So those longshore currents flowing along the coastline, they're curving around and into Delaware Bay. And they make this kind of circular motion, which gives it this, this curve. So we also have all of this is just a barrier island or a sandbar in front of us. And that's protecting all the inlet bays that we have here. So Rehoboth Bay, Indian River Bay, all those rivers that are flowing into the Atlantic Ocean. The mouths of those rivers are kind of protected by this sandbar here. Okay, so let's talk about estuaries. Estuaries they're semi-enclosed, they're bodies of water by the coast, and it's obviously the mouth of the river, where the river is going to meet the ocean eventually. So it's connected to the river because it's connected to the ocean. Because it's connected to the ocean, it's a mix of fresh water and salt water. And because you have that mix, you're going to have a lot of biodiversity. There are certain marsh grasses that can handle periods of saline inundation, so they can survive there. You get waterfowl from freshwater systems that like the area. You get waterfowl from seawater systems like seagulls that come to the area. And you also get a lot of different aquatic life. Some things like to swim into the saline water, spawn, and then swim back, and vice versa. Some fish like to swim into the fresh water and spawn and swim back to the ocean. So you get this really, really diverse boundary between the freshwater ecosystem and the saltwater ecosystem. All right, so let's talk about Delaware Bay specifically. So it's a drowned river valley. So whenever we do all of these sonar studies of Delaware Bay, this is the image that we get back. So what's something that you notice here? You see all these linear trenches along the bottom of around the center of the bay itself. It's really deep near Cape Henlopen. So all of these are just extinct river valleys. At some point in the past, Delaware River, which flows right into Delaware Bay, used to flow all the way out right in between New Jersey and Delaware down to the south. So at that point in time, we had a lot of glaciers. It's the Pleistocene. We've got nothing but ice sheets everywhere. So all that water is locked up in the ice. So the global sea level is lower. When we have a lower sea level, we have a steeper gradient for the water to flow. So it's cutting in and incising that portion of the continental shelf. So that's why Delaware Bay exists, because it had the space and it had the energy to incise into this area here in between Delaware and New Jersey. So it used to be a river valley. Now it's not, because as the glaciers have melted, the sea level is gradually going to rise over geologic time, swallowing up those ancient river valleys and filling in the bay itself. And that's why we have a bay there. Because we incised with the river so much, there was all that space there for the seawater to enter. And that's why we have a bay. So when we're talking about sea level is always changing. So that's where we have relative sea level. So if we're looking at relative sea level, we're talking about your specific location on the coast. So if I went to Lewis, Lewis has a relative sea level. compared to a global average. So Lewis's tidal range is pretty normal for a coastal mid-Atlantic place. Get a range of around, when's the last time I checked their tidal data? Probably a range of about 6 feet. So it's pretty significant. Like if you were standing on one point and water was lapping at your ankles, if you stood there for 6 hours, it would eventually go over your head. Unless you're taller than 6 feet, of course. But it's a pretty steep tidal range. Then you get to the Bay of Fundy in Nova Scotia. This has the highest tidal range at 48 feet. Whenever you dock your boat and tie off your boat in the Bay of Fundy, you have to give at least 50 feet of slack. Otherwise, your boat is going to pull the pier into the bay itself. That's how steep their tidal range is. So you can see at the top, those boats are on dry land right now. 6 hours later, we have them floating in the water. That's a pretty crazy tidal range. So there are a lot of things that control that. Obviously, you can't control the tides because the tides are going to come in, they're going to come out, and that's based on gravity and proximity to the moon, distance to the moon, and the sun as well. But local controls can create a large tidal range as well. The Bay of Fundy is almost a fjord. You've got these real steep, glacially cut cliffs opening up to the Bay of Fundy. So if you limit the space that the water can rise, it's going to rise a lot higher if you're limiting the area. So it's kind of like this bottleneck effect in the Bay of Fundy, which is why they have such a high tidal range. They have a pretty average range under normal circumstances, but because it's all funneled into this one area, you're funneling all that water into a smaller area, you're going to get a higher range in the tide. Okay, so that's relative sea level. Now we're going to talk about eustatic sea level. So this is the sea level from the center of the Earth to the ocean surface, and that's determined by a global average. So we average all of these measurements of sea level all along every coast in the world. We'll eventually get to a global average sea level, and we can calculate that for almost any age and any time. So this is from satellite data. So we only have a limited amount of satellite data. This is from 93. So we can see from 93 to I think that's 2017 for this last one. We have a significant level in the average sea level, eustatic sea level. Got a change of, what is that, 80 meters? 80 meters, Jesus, that would be awful. 80 millimeters, excuse me. So that's probably 8 centimeters. So yeah, so about there. That's what 80 millimeters looks like. Nothing too big, but think of it this way. We're talking about the entire global ocean. So if you have different local side effects that affect your tidal range and your tidal sea level, a global change of that is going to affect your local sea level significantly. So whenever we're talking about eustatic sea level, we're talking about the total volume of water in the sea ocean. Think of the ocean as just one big tub, and we're just living along the rim of that tub. So as that whole ocean water change happens, we're going to experience differences in sea level differently. Okay. So we can compare this to, we have a lot of data that we've collected because we started collecting data in around the 1870s. This is when we realized that having daily tidal data was going to be super important to the future. As you can imagine, during the 1870s, we're at like almost the height of the Industrial Revolution. We're going to have a lot of people caring about shipping, about shipping lanes and avenues. So they're going to care a lot about when the tides come in. That's going to define when your ships go out and when they come back in. So that's why we started collecting all this tidal data. So we have tidal, like in-person tidal data going way back to the 1870. We also have geologic data. based on geologic formations and the timing and relative dating of those, we can tell where the sea level was over geologic time. So we can tell long-term trends through geologic formations. And then once we get into the 90s, we're starting to get more technological, measuring these things from space in a defined orbit. So now we're getting a lot into more definite changes in the global sea level. That's going to enable us to find this 80 millimeter difference from 95 to 2017. Okay, so eustatic sea level is driven by climate change. So, and the climate has changed multiple times over Earth's history. As temperature increases, you're expanding water. So water is, as with any material made of atoms, which is every material, as you melt down things from a solid to a liquid, there is more space between the atoms, right? So as you're creating more space between atoms, you're going to expand the total volume that material is going to take up. So as we're increasing the temperature, we're melting things and we're increasing the volume of the total amount of water. As you're melting ice, ice usually stays on land, but it can also fall into the water. As it's melting, it's going to raise that global eustatic sea level. As it's decreasing, as you can imagine, if we have precipitation on land, it falls as snow. That snowpack gets keeps building up and up and up until it compresses into ice. Now we're locking up all of that fresh water. So we're taking we're decreasing our volume and we're taking it out of the water at the same time. So these changes in temperature on land cause ice to melt, and if it melts, it's going to eventually make its way into rivers down into the oceans. If it stays as ice, it's just going to stay in that one place on the land, right in the glacier. It's not going to go anywhere. It's just going to stay there until the global temperature is hot enough for it to continue to melt. So we can also get ice ages that will decrease sea level rise. We had one in, it was a little one in, I think, 1550, somewhere around there. It's literally just called the Little Ice Age. If you're a student of history, it's a really cool thing to look up because most people say that it was a contributing factor to the fall of the Ottoman Empire, just because they lost a lot of their crops. So there was a lot of tension built up in the Ottoman Empire as a result. We can also get some changes in sea level based on extremely strong storms. So if we have El Nino, La Nina, these are these different oscillations in the Pacific Ocean. They mostly affect South America. They can also affect the southern United States. But these are these really strange oscillations that have this regular decadal pattern. And they bring in a lot of water. They suck up a lot of the water out of the ocean, dump it onto the land. Once it's on the land, it takes a long time for it to get back into the ocean. So that can also influence the global sea level on the short-term timescales, as well as if we have a busy hurricane season like we had in 2020, that can also help to kind of drop the overall sea level by a little bit. But since hurricanes lose all that energy the moment they hit the coast, most of that water is going to flow back into the ocean relatively quickly. It's not all the way up in the Andes. It's on the coastal plain, so it's not going to take much time at all to get to the ocean. So this point right here in 2012, I think, that's where we had a real busy El Nino season, a pretty busy hurricane season as well. So that's where we had that tiny drop off for about a year in the global sea level. Now on the long-term trend, that was just a drop in the bucket. It didn't really matter. But it was interesting to see that these strong storms can influence that sea level change. Okay, so we can also change the shape of the ocean basin and eustatic sea level through tectonics. So as you can imagine, if all of the continents are pushed together in Pangaea, we're going to have a very different sea level. We've got a lot more surface area, a lot less barriers in between the oceans. So we're going to create a very different ocean basin shape. So very, very large portions of the deep ocean on the margins of the planet. As we're spreading those out, we're going to develop more and more mountains. We're going to change areas into mid-ocean ridges. We're going to raise that sea level by pushing all that water up by developing mountains and mountain chains. So we get a lot of influence of sea level rise from tectonics. Now, granted, that's on millions and millions of years in terms of time scale. So not something that we're going to see in our lifetime, more something that we would see in the geologic past whenever we're studying sea level changes. So we know Delaware Bay used to be a river valley. So why is it no longer on land? Was it because of relative sea level change or eustatic sea level change? Yeah, eustatic sea level change. So eustatic sea level change, we're changing the global sea level. If we're changing the global sea level, that's where we're bringing the overall sea level up enough to the point that it can swallow up this huge river valley. It's not going, if we just had relative sea level change, it may affect the very edge of that river valley, but it's not going to swallow it all whole. So eustatic sea level change is why we have Delaware Bay and not a river valley there. Okay, so let's go back to relative sea level. Relative sea level is dominated by waves and tides. So waves, we have a very short period. Remember, when we're talking about period and frequency, we're talking about the actual shape of the wave, the distance between the crests, the height of the crest itself. So we're getting back into the physics here of how waves work. So waves are always caused by wind and the direction of the wind. The frictional force of the wind flowing over the water is going to pull that water. It's going to oscillate into the sinusoidal shape. Tides are a much longer relative period. We have 12 hours to high tide, 12 hours to low tide. So we have these different tidal extremes. That's going to be caused by gravitational pulls. So we have two very large bodies of gravitational force that act upon the Earth. One is the sun, the other is the moon. Even though the moon is smaller than the Earth, it's going to pull and have a gravitational pull on the Earth itself. It's just that the Earth is stronger, so that's why the moon orbits the Earth and not vice versa. It has more mass behind it. So it's a little hard to see, but you have your general shape of the Earth. That gray outline that we have to each of the sides of it, that's the bulge in gravitational pull. So based on where the moon is, it's going to pull the greatest in that direction. So whenever you have the moon, in this case, perpendicular to the Earth, you're going to get the largest tidal bulge is going to be in the direction of where the moon is. That's where the most gravitational attraction is. That's going to give you the highest tide. So as the Earth is going to change its tilt, you're going to get a different tidal force along the entire edge of the Earth, a different gravitational force pulling it. So as you go from winter to summer, you're going to get an overall lower tidal range and then a greater tidal range based on where you are on the Earth. So now we're going to start to interact with the sun as well. So if the moon is directly in line with the sun, we're going to get an overall greater gravitational pull. This happens during the full moon and the new moon. New moons happen because the moon is right in between the sun and the Earth, so it's not getting the reflection of the sunlight. The reason you can see the moon in the sky is not because it generates light, it's because it's reflecting light from the sun. So whenever you see a full moon, it's on the other side of the Earth. It's on the opposite side of the sun. So you're going to see that full reflection of the moon itself. And this is where we're going to get our spring tide, because we're combining the forces of the gravitational pull of the moon as well as the gravitational pull of the sun. You're getting a bigger bulge in the gravitational pull itself, and that's where we get our largest tidal range. This is called the spring tide. It happens at full moons, new moons. We get our greatest gravitational attraction. If we have the opposite, where let's say we're at a quarter moon, and half moon, and let's say that the moon is up closer to the northern hemisphere, so we're getting a pull this way as well as a pull this way. So we're going to lower and decrease that total attraction. Okay. Okay. I don't want to ask you guys this because it's still kind of confusing. So during a neap tide is what we mentioned before. So where we have our half moon, it's pulling in a direction perpendicular to the sun. The sun is pulling this way, the moon is pulling this way. That combination of those two, that's where we get our shortest tidal range. Because we still have gravity pulling on it, it's still going to affect the tidal level, but not as much as if they're pulling in the same exact directions. So just remember, whenever the moon is perpendicular, we're going to get the smallest tidal range. Whenever they're in line, the sun and the moon are in line, we're going to get our largest tidal range. Okay, so let's talk about waves now. And if you guys have any questions about any of this, please just shout out and let me know. Okay. So we know that waves are generated by wind, specifically the friction of the air mass moving over top of the water surface. That's going to eventually pull and create friction that will create these waves. It picks it up in a manner of terms. So if we have low energy wind, like if we look at this graph down here, we're increasing the amount of wind to the right. So lower amounts of wind, we're going to get small ripples, nothing really huge. But as we increase and increase, we're going to go from ripples to choppy waves to fully developed waves that'll eventually come all the way to the shoreline. So if we have an uneven surface, as you can imagine, smooth surfaces don't have a good amount of friction. If we have a very smooth surface, I'm not going to develop friction, but if we have a much rougher surface, we can get a lot of friction. So the less smooth the surface of the water is, the more friction that we're going to develop and pick up that water from the wind. So the less smooth the surface, the bigger the waves, basically. So if we have this change in the wave itself, and we create that wall, that gives the wind something to blow against. So that'll also increase the amount of energy that waves will direct. So all that energy goes from the wind down into the water. So as you can imagine, the two are directly related. You have a higher wind speed, you're going to have a greater wave height. So you're going to get these thick, choppy waves, something you'd see in the movie The Perfect Storm or something like that. Get a lot of storms, they'll make very strong winds, and they can make enormous waves. So large-scale storms like hurricanes, tropical storms, they're going to create the biggest waves and the biggest wave energy. The other thing is wind duration. So the longer that the wind is going to continue to blow, and it's going to continue to build up a larger wave. You have a longer period of time, you're always going to build up larger waves. You can also build up a larger surface area to blow against. So that's where we're going to get our biggest waves. And then, of course, this is a little confusing concept. This is called fetch, which is the distance the wind blows over the water surface, because the wind is not blowing everywhere on top of the water surface. It's only blowing in a certain area. So the larger that area is that the wind is going to enact upon, the bigger waves that you're going to get. So the greater the fetch area, the bigger the wavelength, wave period, and wave height. So these three are all connected. So basically they're all, as you're increasing any of these, increasing fetch, increasing duration, increasing the speed, you're going to get bigger and bigger waves. So they're directly proportional to each other. Okay, so we've seen this before when we were talking about tsunamis. This is what the waves look like in the open ocean. There are all these circular orbits, these like real small oscillations that happen out in the deep ocean. So all the way from the bottom of the ocean to the top, you get these small oscillations that continue to grow larger and larger as you get shallower and shallower. So if you're in the boat and you're looking at the shape of these oscillations, as it's being pulled up, the boat is going to be pulled down. It's going to continue to pull up. You're at the crest of that wave. That's where you're about halfway point through the oscillation. You're going to continue down. You're down in the trough of that oscillation now. So the shape of the boat is making relates to the shape of the oscillations that are creating the waves. And in between each of those oscillations, you have the troughs of the waves. At the crests of those oscillations, you're getting the crest of the waves. So these oscillations continue all the way to the shoreline. And as you can see, once we start to approach the shoreline, we're going to increase friction forces. We're going to increase drag because now we're getting shallower and shallower. There's more stuff on the bottom that we're going to pick up. So we're going to decrease the wave velocity. The wavelength shortens, but we're still carrying the same amount of water. So because we're increasing, we're shortening the wavelength, but we still have the same amount of water, the instability in that wave is going to change. The wave height is going to increase, and that's how you get breakers. It can't handle that all the volume of water it's carrying, so it's going to just break its shape, crash over itself, and break upon the shoreline. So that's why we get the shape of waves. So we have two types of breaking waves. We have plunging breakers. This is the one, if you're a surfer, this is what you want, that picturesque circular shape. They gain and lose height very, very quickly. They're very erosive because all of that water is like acting like an excavator claw, kind of. You get the breaking of the water, it's going to pull in that same circular motion, and you're getting water behind it to enact that force upon that shoreline. So they're very, very erosive. Got a lot of water behind them, a lot of force. And then you have spilling breakers. Spilling breakers, probably better if you're wakeboarding rather than surfing. Real gentle, they spill gently. Because they're gentle, we have less energy. And remember, if we don't have a lot of energy, we're going to deposit sediment. Stuff's going to be able to fall out of suspension, fall out of the forces of that water, and it's going to deposit on the shoreline. So most of spilling breakers, because it's so gentle, that's where we're going to get buildup of the sand deposits along the shoreline. So we get a lot of these more gentle slopes on the beach, as opposed to these more irregular, blocky, erosive features from plunging breakers. Okay, so we've said this before, there are no straight lines in nature, and that is true when it comes to waves. Even though whenever we were talking about tsunamis and how they go outward in all directions from that initial earthquake, as they approach stuff, they're going to encounter a lot more differences in drag and friction, so they're going to change their direction based on that. The energy wants to travel along the path of least resistance, so it's going to be reflective of the surface it's traveling across if it's encountering any resistance. So if we have shallower areas, we're going to have a lot more drag because we're pulling a lot more stuff from the bottom. We're going to increase the friction. And because we're increasing friction, we're going to slow down the overall wave. So that's why in very shallow areas along continental slope, along the continental shelf, because we're much shallower than the abyssal plain, we're going to get a lot more slower waves, gentler waves, and we're generating all of that from friction. If we have deeper areas, like we go to the West Coast where we have just a steep drop off of cliffs, this is where we have less drag because there's not anything on the bottom creating that friction. So we're going to move a lot faster, and if we're moving a lot faster, we have more energy behind us. So more energy, we're able to erode a lot more. That's why we get all these erosive coastlines on the West Coast. So because all this energy is traveling as a wave has a certain vector, meaning it has a direction. So the wave front is the approaching set of waves. As it approaches the coastline, it's going to move in a line. And once it starts to curve, it's encountering all of these obstacles in its way. So it's going to curve around these obstacles because all of this friction is built up in the front. So at the wave front, you see it's going to crash into this sea stack here. So the waves around it are going to curve around, almost hugging the coastline and hugging the sea stack. So here you have wave normals. Wave normals travel perpendicularly to the wave front. So the wave front is moving in this direction. Those wave normals are going to curve around it because it doesn't have that obstacle in its way. It's going to follow the path of least resistance. It's going to curve around it. So that's why we have this headland forming in this direction and forming in this shape, just because everything's curving around that sea stack and eating away at the sides. And that sea stack is kind of protecting that tip of the headland. So that's why we don't get all that erosion at the front of it. We're getting all the erosion on the sides of it. And that's why we get sea stacks forming in these lines, because as we're starting to erode, we're going to develop another sea stack by breaking it apart from the rest of the headland. We're going to continue to erode, and that's why sea stacks are always linear features. They always form in a line parallel to the wavefront. Okay, so another thing we have is wave refraction. So all the energy is converging on an area. Since that area is it's an object in the way, all the energy is going to diffract in and refract in different areas. So on headlands, where we have these almost spear tips out into the sea, we get this convergence of all those wave normals. So they're flowing outward and into the sides of this erosional headland. And that's why you have these cliffs here. Because they're directing their force towards the headland, all their energy is dissipating away from these embayments. So you have these almost wave-shaped headlands. In between those, in the troughs of those, you have beaches where sediment gets deposited. So you have your plunging breakers against the headlands, your more gentle breakers against the beaches. So we're depositing sediment. All that sediment that gets eroded from those headlands is most likely sucked back out and deposited on those beaches there in the center. So we have the increase of convergence, and we have wave height and energy, and they're both going to increase as we approach these erosional cliffs. Okay, and as we mentioned, because those wave normals are flowing away from it, we're going to develop these embayments and beaches where we have less erosion, more deposition. So we're putting sediment there rather than taking it away. Okay, so where is most of the wave energy concentrated? Is it the headland or is it the beach? Go ahead and shout it out. Headland. Why is that?
Because the waves converge and then the beach starts to
Exactly. So the most important takeaway from this is that when we're talking about wave energy, higher energy is going to erode. Lower energy is going to deposit. So based on where you have deposits of sediment, like a beach, those are going to be lower energy environments. If you have higher erosion properties, like at rocky headlands, but no deposition, that's where you're going to have the highest amount of energy. You need energy to erode stuff away. It's a rock. It takes a lot of energy to break it apart. Okay. So this is a third coastal hazard that we have, which is known as the longshore current. So this is a time lapse of Cape Cod. And as you can see, if you're looking at this barrier island over time, it's kind of evolving. It's kind of changing its shape. It's building up sand in different places. And this is all the way back from the 80s. So if you think about anytime you've gone to the beach as a kid and you swim in the ocean, as you're swimming around, you're not really paying attention, and then you look to the shoreline, you see, wow, you're a lot down further than where your parents' umbrellas are. That's the longshore current taking you in that direction. So as the waves come in, there's this long current that is giving a different direction to the waves itself. So if there was no longshore current, the waves would want to come against the shore perpendicularly to the shore at a very almost 90-degree angle. That's the direction it wants to go. But we have this current that's going to create an angle in that wave direction. So it comes at an oblique instead of straight on. So because of that, the wave is going to break at an angle. It's going to break apart. Even in low energy environments, we're going to get some erosion because it's already all this sand that's easy to move away. It's unconsolidated. So we break on the shoreline. As gravity is rolling it back, it's coming back perpendicular to shore. It's going to carry some sediment with it. Then all that sediment is going to come back again with the next wave. It's going to be deposited at an oblique angle again, and it's going to be brought out perpendicularly as the tide comes out, as the wave recedes. And you keep doing that on and on and on. So if you track one grain of sand from one side, that's the direction it's going to move. Oblique in, straight out, oblique in, straight out. So you're going to get this motion of these particles of sand continuing along with the longshore current. So that's why you get this directional movement of what you saw before there it is. So in this case, the longshore current direction is to the south. You can see all that sand building up and being carried down to the south direction. So it's that same wave motion. You're going in, you're crashing against it, you're bringing sand out, going in at an angle, crashing against it, bringing sand out. And you're going to continue all the way down the coastline until you're changing the shape of the coastline because of where the sediment is brought in and where it's being taken away from. Okay. Sadly, the speakers in this room don't work. Skip around. Here we go. Okay. So here we have the wave direction. That first wave came in, it's going back out as it's receding, taking sediment with it, coming back in at an angle, depositing that sediment, bringing some more along with it back out, and we keep going back and forth and back and forth. And that's how we get this long wave motion of sediment all the way down the coast. So as you can imagine, if you're buying beachfront property and you have this beautiful white sandy beach in front of your house, and in maybe a year or so, that sandy beach is not as thick as it used to be, that may lower your property value. So a way that they decrease this is, you can thank the French for this word, this is called a groin. It's literally just a wall of steel and rock and wood, and it just prevents a lot of that longshore erosion. So you get some more deposition along those along those groins, and then there's a little winnowing out. But there are also problems with that because, as you can imagine, rich people that own beachfront property don't want to see all of these engineered structures along the beach. So they would rather have just this perfect beach. So a lot of people do beach renourishment, which we'll get into. So longshore currents create what we know as longshore drift. Drift is just the sediment that's moved by the current. So as it goes from one side of the beach to the other, that's that longshore drift. So beach drift is where it's, you have the breaking of the wave, you're carrying up all that sand outward. Longshore drift is the cumulative effect of that. If you add up that beach drift over a long period of time, where is all of that beach drift going to end up eventually? That's the longshore drift. So this is where we get stuff like Cape Henlopen. So Cape Henlopen, the longshore current is up to the north, right at the spit. So all of that stuff from the south, all that sand is being pulled up and up along that longshore current until it gets to a point where there's no more shore left. So it has to deposit somewhere. So it's depositing right on the tip of the shoreline. It's going to continue to build and continue to build, and it's going to elongate that bay. So if it has enough time and it has enough sediment deposits, it could eventually close up Delaware Bay if it wanted to. And if you gave it enough time, it would eventually just keep building up and create this huge barrier island covering up Delaware Bay. Now, obviously, due to human engineering, we're not going to let that happen because Delaware Bay is a really important economic avenue. Port of Wilmington has a lot of economic value. Philadelphia as well, most of New Jersey. So they're not going to let that happen. So that'll be human engineering that influences that. But if in a natural system, you give it enough time, it's going to block that off, and that will eventually make Delaware Bay a lagoon instead. And then once you have that, you're going to change the way sediment interacts in that environment. It could eventually fill up. Okay, yeah, we mentioned that. Okay, where are we? We're at slide 59, okay, let's end early today, just so we'll have some stuff to talk about for coastal hazards tomorrow. Once again, if you have any questions on this stuff or stuff for exam 2, please let me know. Set up an appointment in office hours, or just come to my office hours tomorrow from 4 to 5 or Wednesday 4 to 5, Penny 204. And if you have any questions about Canvas, if there was stuff that was wrong on Canvas, I think some of you mentioned reading assessment 6. I believe I fixed that, so it should be good. If it's not good, let me know, and I'll reassess it. Canvas is nothing if not annoying. So I'll continue to fix it as needed. But have a great Monday, and I'll see you all tomorrow.
Thank you.
Yeah, how's it going?
I'm Ryan.
Yeah.
For the exam.
Yeah.
I'm kind of curious about that. I should have just emailed it, but I was overthinking about it. So I was out for like the second half of last week. Did I mind retaking it?